What are we going to do with this limit? I've got the limit as x goes to infinity of x to the 1 over x squared. As I plug infinity in, I get infinity to the 1 over infinity squared. This 1 over infinity squared goes to 0, and I get infinity to the 0, which is an indeterminate form. Sounds like a job for L'Hopital's rule, but L'Hopital's rule needs the limit to be in the form, so f over g needs to either go to 0 over 0 or plus or minus infinity over infinity. That's not what I've got here, but if I apply a logarithm, I can bring that 1 over x squared out in front, and that's exactly what we're going to do. So let's apply a logarithm. Before I do that, I'm going to go ahead and sneak in a y equals over here, so I can take the natural log on both sides. So I end up with the natural log of y is equal to the natural log of my limit. So limit as x goes to infinity of the x to the 1 over x squared. I can bring that natural log inside of the limit, which is where the magic starts to happen. Okay, so x to infinity. I have my natural log of x to the 1 over x squared. Well, I've got a power inside that natural log, so I can bring the power out in front. This gets me really, really close to being able to satisfy the condition of L'Hopital's. So I still have this limit out in front. X approaches infinity, but I can move the 1 over x squared in front of the natural log of x, and I can rewrite this. So limit as x goes to infinity, still have not applied that yet, of the natural log over x squared. Now let's take a look and see what happens when we apply infinity. So when I put infinity in, I end up with the natural log of x going to infinity. And then the denominator, infinity squared, is infinity, and I've satisfied the condition of L'Hopital's. I can go ahead and take the derivative of the numerator and the denominator. Let's do that. Love L'Hopital's rule. I'm going to put a little LH on top of this so you can see that I've applied that. Back to my limit. So limit as x approaches infinity, the derivative of the natural log is a 1 over x, and the derivative of x squared is a 2x. So as I simplify that down, x approaches infinity, I get a 1 over 2x squared. As I substitute infinity in, I analyze this and I end up with 1 over infinity, which goes to 0. But it is not the original limit that I was looking for. What goes to 0 is the natural log of y. Y was the original limit. So I need to exponentiate both sides here. So I'm going to exponentiate both sides base e. I can cancel off the e and the natural log, which tells me that y, which was my original limit, is equal to e to the 0, and e to the 0 is equal to 1. So the limit as x approaches infinity of x to the 1 over x squared is equal to 1. Here comes our next example. In this one, we're approaching 0 instead from the right because of the domain restriction, and I've got x to the square root of x. As I attempt to substitute in 0, I end up with 0 to the 0. This is another indeterminate form. It's sort of like which one wins, right? The base of 0, which multiplies over and over and over to get me a result of 0, or the power 0, which typically gives us an answer of 1. Well, I again notice that I've got this exponent here, and I'm going to go ahead and use the logarithm so that we can work our way to one of these indeterminate forms. So I want to start by taking the natural log on both sides. So I've got the natural log of y, which is my limit, is equal to, let's go ahead and bring the natural log inside the limit to start here. So the limit as x approaches 0 from the right, natural log of x to the square root of x. Actually, lots of shortcuts that you can take. I know that that power is going to come out in front of the natural log. That is going to get me to a place where I can get a quotient out of this guy. So I get the square root of x, natural log of x. Well, the square root of x is actually an x to a 1/2 power. If I want to put that into a denominator, I'm going to put it into a denominator as an x to the negative 1/2 power. As I test to see if this satisfies the condition of L'Hopital's rule, I want to think of this as the natural log of x over 1 over radical x. Let's go ahead and plug 0 in from the right. Well, 0 from the right, the natural log goes to negative infinity, so I get a negative infinity there in the numerator, and I've got 1 over x inside that square root. That's going to be a 1 over radical 0, which goes to infinity. So we do end up satisfying the condition of L'Hopital's rule. Let's go ahead and take the derivative of the numerator and the denominator. Still have not applied my limit, so x approaches 0 from the right. The derivative of the natural log is 1 over x, and the derivative of x to the negative 1/2 using a nice power rule, that's going to be negative 1/2 x to the negative 3 over 2. So simplifying, I end up almost to a place where I can take that limit. X approaches 0 plus. I have a 1 over x, let's call that an x to the negative 1. I also have an x to the negative 3/2. I'm going to pop that up into the numerator as a positive 3/2, and I've got that negative 1/2 out in front. So I've got a negative and a 2 there. This is going to give us actually a pretty nice expression to evaluate. As I simplify that, I can just add those exponents up. X approaches 0 from the right. X to the negative 1, x to the 3/2, adding those exponents gives me an x to the 1/2, or you could write that one as a square root. I still have my negative and my 2 there, but as I plug 0 in now, it is defined, and this guy goes to 0. But what goes to 0? The natural log of my limit goes to 0. So I need to exponentiate both of these base e to undo the natural log. So y, which is my original limit, actually goes to e to the 0, which is equal to 1. Lots more videos where this came from. Thank you so much for watching.